Hello, the Math Dog here. In this video, I'm going to simulate an AP Calculus question, a free response question that involves accumulation functions, the second fundamental theorem of calculus, finding first and second derivatives of accumulation functions, and using geometry to find the area under a curve. So I call it simulated because it is like an actual AP question from the AP Calculus curriculum. This will be a no calculator question. So let's get started. This simulated free response question involves working with the following topics from the AP Calculus AB curriculum, AB being like Calculus 1. Accumulation functions, which are actually a very big thing in the AP curriculum. Using geometry to find the area under a curve, which is integrating using geometry to do the integration. Applying the second fundamental theorem of calculus. Determining whether an accumulation function has a relative maximum, minimum, if any, in fact, exists at all. Determining if an accumulation function has an inflection point, and if so, where are they located. And in general, being able to work with first and second derivatives of accumulation functions when being presented with a graph. So these are the things that this question will cover. Let's move on. So first we'll do a couple quick reviews before we get started on this question. So let's assume f is an antiderivative of big F is an antiderivative of little f. Thus, capital F prime of x will equal f of x. So this is we're going to derive here the second fundamental theorem of calculus quickly. So the derivative with respect to x of the integral from a to x f of t dt is going to equal, okay, and then dt is called a dummy variable. Actually, the variable we're working with in the problem actually is x. So what I'm going to do here is, before I take the derivative, I'm going to integrate this accumulation function here, which is going to be the antiderivative again of little f is capital F. So this is going to be capital F of x minus capital F of a from the fundamental theorem of calculus. So we now will take the derivative of this. So I can distribute the derivative. This is the derivative with respect to x of capital F of x minus the derivative with respect to x of capital F of a. Well, the derivative of capital F of x is capital F prime of x, and then this is a constant, so that's going to be 0. Well, capital F prime, because f prime of x right here I said is little f of x, this is our result. So the second fundamental theorem of calculus, which is, this is the form that the AP Calculus curriculum uses. There are more elaborate forms, but this is what you need to have memorized for the AP test. This will show up a lot on the AP exam. So this is just going to be little f of x. You could have then, sometimes you're going to have a thing where you have g of x up here, and that's a little different, but I'm not going to do that in this problem. So this is the result we're going to need here. This is going to be this. All right, then also I'm going to be using this property here of integrals. So I'm going to show why this is true. The integral from a to b of f of x dx is equal to the negative of the integral from b to a f of x dx. So I've swapped the upper and lower limits and put a negative sign out front. So let's see why this is. So the first, what's on the left of the equal sign here, by the fundamental theorem of calculus, is capital F of b minus capital F of a. And again, we're assuming capital F is an antiderivative of little f. But then this on the right side, notice what this equals. Again, by the fundamental theorem of calculus, this has to equal the negative of capital F of a minus capital F of b. But now applying the negative sign in the distributive property, this is going to be negative negative, so that's f of b minus f of a. So we've shown that, in fact, when you swap the upper lower limits, you got to put a negative sign in front. But these, in fact, are equivalent expressions. So let's do a function f that's continuous and differentiable on a interval. So I've just drawn some sketches here to review f prime and f double prime. So if I have a function f that looks like this in this interval, the slope of the tangent line is positive, so the first derivative is positive because that's what the first derivative measures. Second derivative measures concavity. So if I take 2 points on the interval, if I draw a line segment between them, and it is above the curve, then it is concave upward. The second example, the slope of the tangent line is positive, but so that's why f prime is positive everywhere, but it's concave down because a line segment I connect between any 2 points will be below the curve. Then the third example, the slope of tangent line now is negative, and it opens upward because, again, a line segment I connect to 2 points, it's above the curve, so the concavity is positive, and the derivative, or the slope of tangent line, is negative. In the last example, the slope of tangent line is negative everywhere, and it's concave down because between any 2 points on the interval, the curve, or the line segment connecting 2 points on the curve, is below the function. So now let's take a quick look at inflection points. You can have a bunch of situations here. I'm just going to look at a continuous function. So the first one, this is like the function f of x equals, well, this is actually a slope, say, could be 1 even. So the inflection point is where concavity changes. Notice it goes from concave down to concave up at the inflection point. The second derivative will have a value of 0 at the inflection point, and the first derivative is greater than 0. The second example here is like the function f of x equals x cubed. So at the inflection point, the second derivative is 0. It goes from concave down to concave up, but the slope of tangent line at that point actually is 0. And finally, I have, like, this is like the function f of x equals cube root of x. Here, the concavity changes, so f prime double prime is 0, but the function goes vertical at that point. Remember, the slope of a vertical line does not exist, so the first derivative actually does not exist at that point. Just a little reminder here of the relationship between functions, first derivatives and second derivatives. So I always believe it helps to be able to picture these things in your mind. Alright, so here's our sample question. So we have a graph here on a coordinate axis. So this point is -6, -2, -3, -3. This is -2, 0, 0, 2, 2, 0, and this is the point right here, 6, 2. I should have another parentheses there. Okay? So let f, this will be our function f, be the continuous function defined on the closed interval -6 to 6, whose graph consisting of line segments in a semicircle centering at the origin is given by the function g of x. This is an accumulation function. G of x equals the integral from -2 to x of f of t dt. Now this is a semicircle here. I sketched it. It's a semicircle. This is a line segment, line segment, line segment. Okay, so part A says find the values of g of 4 and g of -3. So let's start with g of 4. So g of 4 is literally just plugging in for x the value of 4. Okay, f of t dt. Now this is a geometry question now because it's saying find the area of the curve from -2 to 4. Okay, find the area under the curve from -2 to 4, which is from here to here. So we're talking about this area right here. Okay, now you could clearly see, but I'm going to actually calculate the equation of line. This problem you could actually do visually, but sometimes the AP test doesn't allow you to do that. So I'm actually going to show the equation of line and then show how I know what this actually, it is going to be 1, but I'm going to show you how to, just to remind you how to do that if it wasn't exactly 1, like maybe it was 1 1/3. So this is a semicircle. So remember, the area of a circle is pi r squared. So remember, A is pi r squared, but this is a semicircle, so the area, I'll call this of 1. This will be 1/2 times pi. The radius here is 2, so that's 2 squared. Well, that's going to be 2 pi. Okay, so this part 1 is 2 pi. The second part, a sub 2, I'm going to do it first, then I'm going to go through again how to find that if you didn't know what that point was. Well, that's going to be a triangle. Area of a triangle is 1/2 base times height, so that's going to be 1/2 of 2 by 1, which is 1. So the actual area here for g of 4 then is going to be 2 pi plus 1. Now, how could I find this if I didn't know that? Well, I would make a slope table. I would go, okay, this is x, this is y, this is x, this is y. So this is the point 2, 0. This is the point 6, 2. Okay, the slope, change in y over change in x, is 0 minus 2. I'm going to go this way, over 2 minus 6. Okay, well that's negative 2 over negative 4, which is a half. Okay, so we have y equals 1/2 x plus b. Okay, so I've got y equals 1/2 x plus b. I'm going to plug in one of the points on this line segment, 2, 0. So when y is 0, x is 2. So solving for b, that's going to be 1. So b, I have 0 equals 1 plus b. So b is going to be negative 1. Okay, so I have the equation of, this is the function f here. So in this little segment here of f, because this is a segmented function, so this is going to be f of x equals 1/2 x minus 1. So at 4, which is because I want to find the height of this graph right here. That's what f is. It's the height of the graph from the, in this case, the x-axis, which is the line y equals 0. So this is going to be 1/2. F of 4 then is going to be 1/2 times 4 minus 1, which is 2 minus 1, which is 1. So the height of the graph there is 1. Then we go back. We can then go back and do what I did earlier here. 1/2 times 2 times 1 equals 1. And some of you could be going, well, this is just overkill. Why am I doing this? Well, I'm going through this here because, frankly, a lot of students get 1s and 2 on the AP exam because they actually may understand the concepts, but their basic algebra arithmetic skills are still very faulty, and they don't pass the test because they don't have those skills. So I'm just reviewing, because there are questions on the AP exams where actually it's not going to be immediately obvious what this point is here. Anyway, let's continue. So we now know that g of 4 is 2 pi plus 1, because the area of this triangle was 1 and this semicircle area was 2 pi. So now let's find g of negative 3. Okay, well, g of negative 3 here is going to be the accumulation function from negative 2 to negative 3 f of t dt. Okay, well, I like to do my functions where the smaller numbers in the lower limit and then the upper limit is going to be larger than the lower limit. So I'm going to take the negative of, swap these, of the integral from negative 3, let's do that again, negative 3 to negative 2, f of t dt. So when I swap the upper lower limits, I must put a negative sign out there. Okay, so now let's look at the geometry of the situation. Okay, so from negative 3 to negative 2, we're talking about right here. And this one, I am just going to use the geometry. I'm going, okay, it goes right through these 2 points. So that's a triangle. The base is 3, the height is 1, so that's going to be 1/2 of, this would be the negative. And by the way, the curve is under the x-axis here, so it's going to be a negative area. But this is going to be the negative. This is going to be the negative of, and again, this is 1/2. I'll call the base 3. And that's going to be negative because it's going to be a negative area because it's under the x-axis. So it's going to be negative 1/2 times 3 by 1. Base 3, height 1. So in the end, though, double negative makes positive, so my answer is going to be 3/2. So g of negative 3 is 3/2. So that's part A of our question. Part B, I'm going to copy the graph so I can do it again. So if they exist, find the value of g prime of 5 and g double prime of 5. Okay, well, let's remember what our function is. Okay, our function is accumulation function. It's right here. I'm going to write it here again. It's going to be the integral from -2 to x f of t dt. So this is what g of x, this is how g of x is defined. It's defined as this. Okay, so g prime of x is the derivative with respect to x of the integral from -2 to x f of t dt. Well, we just did an example review of the second fundamental theorem of calculus, which is what this is. So this is g prime of x then must equal f of x. Okay, and this, by the way, again, is the function f. Okay, so if I'm asking you to find g prime of 5, g prime of 5 must equal f of 5. So all I'm doing is I'm going to the function. I look at the value of f right there. Okay, that's what I want. I want to find the height of the graph at this point. Well, let's go back to what we just did a moment ago. We know the equation of this line is y equals 1/2 x minus 1, or f of x equals 1/2 x minus 1. So f of 5 here has to equal 1/2, I'm using this equation, 1/2 times 5 minus 1. Well, that's 5 halves minus 2 halves is 3 halves. So f of 5 is 3 halves. Okay? Then g double prime of 5, well, if g prime of x equals f of x, then g double prime of x has to equal f prime of x. Well, what's f prime of x? It's the slope of the tangent line. So the g double prime of 5 equals f prime of 5, which is the slope of the tangent line of the graph of f at 5, and we just found the slope of this to be 1/2. 2 over 1 up. So our answer there is 1/2. Okay, let's continue. Part C. Find the x-coordinate of each point where the graph of g has a horizontal tangent line. For each of these points, determine whether g has a relative maximum, relative minimum, or neither. Justify your answers. Okay, so where g has a, in other words, where g has a horizontal tangent line, that means, first of all, tangent lines are the first derivative, so I need to, that's going to be g prime of x. Okay, and I want to know a horizontal tangent line has a slope of 0. Horizontal lines have a slope of 0, so I want to know where g prime of x equals 0. But remember, g prime of x is equal to f of x. So what I want to know is, where does f of x equal 0, first of all. So let's circle those. So f of x equals 0 right here and right here. Okay? Now, for there to be a max or min, let's look at just a simple function here, f. So f, that's a maximum where the first derivative goes from plus to minus. That's a relative max. It's a relative min when it goes from negative to plus. Okay, so this is a differentiable function. So right here, f is going from negative to positive. So right there, that's at x equals, let's write that, we didn't write that down, did we? That is at x equals -2. Okay, and f goes from negative to positive. In other words, g prime goes from negative to positive. So that has to be, this case, that's a relative min. Okay, that's my justification. Okay, now the other one, right here, f is positive because this, we're talking about not the slope of f, we're talking about f, and f is equal to g prime. So slope stays positive. So it's neither a relative max or min because it's not going from plus to minus or minus to plus. So it is neither. So at x equals 2, it's a horizontal tangent line, but there is no relative min or max. Okay. There's an example of horizontal tangent line right there, and that's not a relative max or min. So it could be something like that. All right, let's move on. All right, so the last part of this question asks, on the open interval from -6 to 6, find all values where the graph of g has an inflection point. So inflection point you find from the second derivative, g double prime. Well, what is g double prime? Remember again, this is the graph of f, okay? So we found that g prime of x was equal to f of x earlier. We also found that g double prime of x, therefore, has to be f prime of x. And what is f prime of x? Well, that's the slope of the tangent line to x. Inflection points then are found where the concavity goes from negative to positive or positive to negative. So first thing I want to do is I want to find where g double prime goes from negative to positive, but that's the same as f prime going from positive to negative. So where does that happen? I'm going to circle that. So right here, this is f prime. This is the function f, but f prime is negative here because the slope of tangent line is negative. Then it goes to positive here. So right there is an inflection point. Right here, the slope is positive. Right here, it's negative. There's an inflection point right there. Okay, here it goes from negative to positive. So there's an inflection point there. So far, we have values of x. Those are the values of x. So here we go from negative to positive, so that is at x equals -3. Then we have at x equals 0. Then we have at x equals 2. So g has inflection points at all those points because here it's going negative to positive. G double prime is going from negative to positive, or f prime is going from negative to positive because g double prime is equal to f prime. Here g double prime goes from positive to negative. F prime goes from, I say positive negative, it goes from positive to negative. F prime goes from positive to negative. And then finally here, F prime and G double prime go from negative to positive. Well, that's it for this video. If you found this video informative and you liked it, please give it a thumbs up and please subscribe to my YouTube channel, The Math Dog. You may share the content of this video with others. I will be doing a playlist on AP Calculus free response questions. This is the first one, but I plan to do more, and I have quite a bit of experience with this. I hope, again, that you found this helpful. And if you're taking the AP curriculum, be sure you know your basic algebra and things and go through that and make sure that you can do it quickly, because actually that is a key component of the test, as well as the concepts. Thank you and have a good day.